Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we look at the concept of linear independence. We've already looked at linear combinations. So when you have a set of vectors here we have n vectors labeled u1 up to un. This set is said to be linearly independent if you can't write any of these vectors as the linear combination of the others. So mathematically, a set of vectors is linearly independent if and only if it satisfies this definition. And that is that something times the first vector plus something times the second vector and so on can equal the zero vector if and only if each of these scalars is zero. That's just a formal mathematical way of checking whether any of these vectors can be written as a linear combination of the others. So we're going to look at R3, which I introduced in a previous video. Remember, that's basically the set of all points in the Cartesian plane in 3 dimensions. Now, if you have a set of 3 vectors that's linearly independent, then these vectors span and form a basis for R3. What that means is that any vector in R3 will be able to be written as the linear combination of those 3 basis vectors. Consequently, it means that if you have a set of any more than 3 three-dimensional vectors, it can't be linearly independent. So let's just look at a very quick example. So the standard vectors we use in R3, 1, 0, 0, 0, 1, 0, and 0, 0, 1. This set here constitutes a linearly independent set. None of these vectors can be written as a linear combination of the others, and any vector in R3 can be written as something times this one plus something times this one plus something times this one. On the other hand here, these 3 vectors do not form a linearly independent set. They're linearly dependent. This one is just the sum of these 2. So you can write this vector as something times the first vector plus something times the second vector. Consequently, these 3 vectors do not span R3. Their span would be a 2-dimensional plane going through the origin, and there will be vectors in R3 that can't be written as something times this one plus something times this one plus something times this one. All right, let's solve some problems. So we're going to determine whether or not these 3 vectors form a linearly independent set. So in the previous example I gave, it was kind of obvious that they weren't. Here, it's not at all obvious whether or not they are. So a very useful fact we can use is that a matrix is invertible if and only if its columns are linearly independent. So how could that possibly help us with these vectors? Well, what we're going to do is we're going to combine them into a matrix A, and its columns are going to be U, first column, V, the second column, and W, the third column. Realistically, it matters not at all whether you switch around the columns and have V, W, U, we'll still get the same answer. So how can this help us? Well, these 3 will form a linearly independent set if and only if this matrix is invertible, and that occurs if and only if its determinant is 0. So we're going to calculate the determinant of this matrix. If it's 0, then the matrix is singular, and this set is not linearly independent. It is linearly dependent. On the other hand, if the determinant of this matrix is any number other than 0, then these 3 do form a linearly independent set. So let's go ahead and calculate the determinant of A. So if we remember how to do this, we look at this entry, we kind of cross out the row and column in which it is, and we multiply the number we've circled by the determinant of the resulting matrix. So it will be 1 times the determinant of the 2 by 2 matrix that's left. Okay, now we always alternate signs. So first one was positive, the next one's negative. We circle this. If we cross out the column and the row in which this number is, we're left with a 2 by 2 matrix. So we multiply -4 by the determinant of that matrix. And again, remember the alternating sign. So the last one's going to be positive. It's going to be +3. If we cross out the row and column in which that occurs, we're left with the 2 by 2 matrix 2, 0, 3, 1. Now this helps us because remember the determinant of a 2 by 2 matrix is AD minus BC, where it's A, B, C, D. So the determinant here of this first matrix is 0 minus 2, -2, and 1 times -2. Then we have +4, obviously because 2 minus is here. Now the determinant here is 2 times 0 minus 2 times 3, so that's -6. And finally, for the last one, it's 3 times, the determinant here is 2 times 1 minus 3 by 0. It's just 3 times 2. So that gives us an answer of -20. The determinant here is not 0. And whenever you have a non-zero determinant, it means that A is invertible. And what it means is, in fact, yes, these three form a linearly independent set. That means they will span R3. So because these three vectors are linearly independent, we answered that question in the affirmative on the previous slide. That means that you can take any vector in R3, like this one, and write it as a linear combination of those three vectors. So we know that there will be a solution A, B, and C to this equation, and moreover, it will be unique. So let's look at the first component in each vector. We have 1 times A minus 4 times B plus 3 times C. Looking at the second components, we have 2A plus 2C. And then the third component's 3A plus B. And that has to give us 1, 0, 0. So let's look at the second and third components because they're a bit easier to work with. So if 2A plus 2C equals 0, that means 2A equals -2C, A equals -C. So from the third equation, we have 3A equals -B, or B equals -3A. We can take each of these two and substitute them into this equation here. So doing that, we have A. Now B was equal to -3A, so this will become 12A. 3C will become -3A. That is equal to 1. So seeing this, we get 10A is equal to 1, which means A is 1 over 10, or 0.1. C was equal to -A. And B is equal to -3 over A. So we have found values A, B, and C, and we found them uniquely, which you can always do when the three vectors are linearly independent and form a basis. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.